Hello students, how are you all? In last class you learned general properties of D block elements. So today's topic is F block elements. Now let's look into the what are the F block elements. The F block elements are defined as the elements in which your last electron enters into F orbital are called as F block elements. So in F block elements, last electron enter into anti-penultimate shell. Electrons enter into anti-penultimate shell F orbitals. Nothing but n minus 2 F orbital. Last electrons enter into n minus 2 F orbital. Nothing but anti-penultimate shell F orbitals. So look at the definition of F block elements. The elements in which last electron, the elements in which last electron enters into F orbitals. The elements in which last electron enter into F orbital, that is nothing but n minus 2 F subshell. This is nothing but anti-penultimate shell F orbital. Anti-penultimate shell F orbital are called F block elements. Are called F block elements. This is the definition of F block elements. The F block elements are also called as inner transition elements. Next point, these are also called as inner transition elements. So these are also called as inner transition elements. And the next point is the F block elements. The F block consists of two series of elements. F block consists of two series of elements. They are the 4F series and the second one is 5F series. Look at here. So from cerium to lutetium, this series is called as a 4F series. This is the 4F series. And the thorium to lawrencium, this is a 5F series. This is 5F series, 4F series, and this is a 5F series. So next point is F block consists two series of elements. F block consists two series of elements. They are, the first one is 4F series. The first one is 4F series and the second one is 5F series. 5F series. Even in 4F series or 5F series, last electron enter into F orbital only. So why do we call them as a 4F? Because last electron enter into 4F orbital. In this F block elements, if the last electron enter into 4F orbital, we have to call them as a 4F series element. In F block elements, last electron enter into 5F orbital. So last electron into 5F orbital, we have to call them as a 5F series. Next, the 4F series is also, 4F series is nothing but we have to call as lanthanides. These are lanthanides. 4F series elements are called as lanthanides and the 5F series elements called as actinides. So 4F series elements are called as lanthanides and the 5F series elements are called as actinoids. Next, let us look at the position of these F block elements in a periodic table. In a periodic table, F block elements are placed at the bottom of the periodic table. In a modern periodic table, F block elements are placed at the bottom. So now let us look at what is the exact position of these elements in a periodic table. Now I am taking D block elements. So imagine this is the D block. So this is the D block. I am taking D block elements. Right, in the D block first starts with the third group. This is the third group. Next we have is a fourth group. So this is the third group. Next we have is a fourth group and so on. 3, 4, 5, 6, 7, 8, 9, 10, 11 and I'm taking just last one is a 12th group. Understanding purpose. Now the elements present in the third group. What are the elements present in the third group is scandium, yttrium, lanthanum, and actinum. Scandium, yttrium, lanthanum and actinum. And the element present in the fourth group is titanium, zirconium, hafnium and rutherfordium. Titanium, zirconium, hafnium, rutherfordium present in the fourth group. Now atomic numbers of these elements we have taken. Atomic number of scandium is 21. So to this 21 we have to add 18. So 21 plus 18 we are going to get 39. Atomic number of yttrium is 39. To this 39 we have to add, for the first element we have to add 18, we will get second element. To the second element we have to add 18, we will get third element. So 39 plus 18 we are going to get 57. So lanthanum is 57. To this 57 we have to add 32. So 18, 32. So 57 plus 18 we are going to get 89. Atomic number of actinum is 89. Next we will write the atomic numbers of fourth group elements. So titanium is 22. To this 22 we have to add 18. So 22 plus 18 we will get 40, isn't it? To this 40 next we have to add 18. Sorry, to this 40 we have to add 32. Then we get atomic number is 72. To this 72 we have to add 32. We are going to get 104. Atomic number of Rutherfordium is 104. So what is the point is between the lanthanum 57 and hafnium 72. Between these two elements some elements are missed. So 57, 58, 59, 60 actually we have tried, but in 57 directly we wrote 72. 57 after we wrote 72. That means between the 57 and 72 some elements are missed. Those elements are none other than this 4F series elements. The elements are none other than 4F series elements. So here is same is 58. So 58, 59, 60 and so on. Here we are going to get is 71. 71. Look at this. Here is 58, 59, 60, 61 and so on. Finally get 71. So 57, 58 present in the F block and 71 present in the F block and 72 present in the D block. 72 between the 57 and 72 some elements are there. The elements are present in the F block. So in 57 and 72, the last electron enter into the D orbitals. In these two cases, last electron enter into D orbital. But in these elements, the last electrons enter into F orbital. Cerium to lutetium, the last electrons enter into the F orbital. So that we took here is separate. Next, atomic number of actinum is 89 and rutherfordium is 104. Between the 89 and 104 some elements are missed, 14 elements are missed. So 89 next we have read 90, 91, 92 and so on up to 104 we have read. There are 14 elements are missed. Those 14 elements is none other than thorium. Thorium atomic number is 90. Atomic number of thorium is 90 and lawrencium atomic number is 103. So here is 90 to 103, these are 14 elements. So these 14 elements actually we have to place between actinium and rutherfordium, but we are taking separately because in actinium and rutherfordium last electron enter into D orbitals. In actinium and rutherfordium last electron enter into D orbital. But in thorium to lawrencium, last electron enter into F orbital. So that we brought these elements separately and we make one is 4F series and another one is 5F series. So these elements are placed after these are the elements present at after lanthanum. We are calling as lanthanoid elements similar to the lanthanide. And these elements are present after actinium. Actinium 89, 90, 91, 92, 93 and so on 103. So we are calling them as actinoids, lanthanoids and actinides. So this is the position of F block elements in the periodic table. In periodic table, F block elements are placed at the bottom of the periodic table. So there are two series of elements here. One is the 4F series elements, another one is the 5F series elements. 4F series elements are also called as lanthanoids and the 5 series elements are nothing but actinides. In 4F series, last electron enter into F orbital, 4F orbital. In 5F series, last electron enter into 5F orbitals. So next here is n minus 2f orbitals stands for n minus 2f orbital stands for anti-penultimate shell. So for this case, I will give one small example. This is the nucleus. This is the first shell. This is the first shell. This is the second shell. This is the third shell. Fourth, fifth, and sixth shells is there. Imagine there are 6 shells. So this is the last shell. This is nothing but valence shell. So this is number is 6. And this number is 5. This number is 4. Suppose if you want to get a fourth shell, So how to take n is equal to how much we have taken is n is equal to 6. Suppose if you want to, this is the 4f octal is present here. So how to get the 4f octal? If you want to find the 4f series, 4f octal will be required. So how to get the 4f octal? N is equal to how much is here? 6. So n minus 2 f orbital. N minus 2 f orbital. N is equal to how much here? 6 is there. That is equal to 6 minus 2 f orbital. That is equal to 4f orbital. So I think that what I mean is, so n minus 2 is nothing but anti-penultimate. This is the ultimate shell, this is the penultimate shell, and this is anti-penultimate shell. Anti-penultimate shell is showing in the form of n minus 2 f orbital. Here n is equal to outermost energy level. Last energy level we have to take n value, and n minus 2 represents anti-penultimate shell. In the case of f also, f also you have to take similarly. So this is the f block elements. Next, electronic configuration of lanthanides. The general electron configuration of f block elements is n minus 2 f 1 to 14 ns n minus 1 d 0 to 1 n s2. So this is the general electronic configuration of f block elements. This is for f block elements. The general electron configuration of f block elements. Here n minus 2 f stands for anti-penultimate shell. Anti-penultimate shell. And here n minus 4 stands for penultimate shell. Penultimate shell. Here ns stands for meaning is outermost shell. This is outermost shell. Already we know very well this terms. Next, let us look at the electronic configuration of lanthanoids. First element is already wrote the symbols of lanthanoids. 4f series elements. Atomic numbers. Atomic number series is 58, and next one is Rational name is 59. So 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70 and 71. So these are atomic numbers of these elements. Next, electron configuration of Ln plus to Ln plus. We are taking here is lanthanide elements. We are taking Ln. So it means no electrons lost. Here is after lossing of the electrons. Ln plus in the sense after lossing of 3 electrons. 3 cases we have to get electronic configuration of these elements. Ln. So noble gas we have taken is helium, and this is 4f1. So 4f1, 5d1, 6s2. This is the electronic configuration of series xenon 4f1, 5d1, 6s2. Next, electronic configuration of praseodymium is xenon. So 4f. This d electrons also we have to add. This will be 4f2. F2 and 2. This one electron we have to increase. Then this is 4f3. So 4f3, 6s2. So this is the electron configuration of praseodymium. Next, xenon 4f4, 6s2. Next, xenon continues we have to increase the number of electrons in the f orbital. So 4f5, 6s2. So xenon 4f6, 6s2. Xenon 4f7, 6s2. Next, xenon 4f7. Actually, we have to write 4f8, but here is because of half-filled electron configurations are more stable. Because of that reason, we are taking here is 5d1, 6s2. Next, xenon 4f, this electron identity 4f8, then will become 4f9, 6s2. Next, xenon 4f10, 6s2. Next element, xenon 4f11, 6s2. Xenon 4f14, 6s2. So 4f11. Next we have to take 12. The next 4f13, 6s2. Next, ytterbium. Xenon 4f14, 6s2. 4f14, 6s2. Next we have is lutetium. Xenon Already 4s orbital is completely filled. Then we have to get 4f14, 5d1, 6s2. So this is the electronic configuration of general electronic configuration of lanthanide. So we will take Ln plus 2. So we have to remove the 2 electrons. So we have to remove the electrons. First we have to remove the electrons from the outermost energy level. We have to remove the electrons from the 6s orbital. First 2 electrons we have to remove. Then the configuration will become 4f4. These electrons we have related energy will be changes. So 4f, this will become 2. So 4f2. Then here is a 4f3. Then we have to remove 4f4. This is a 4f5, isn't it? 4f5. Next 4f6. 4f6. Here is a 4f7. Here is we have to remove the electrons. This will become 4f7 5d1. 4f7 5d1. So this is a 4f9. This is 4f10. 4f11, 4f12. Continuously you can take 4f13. So 4f14. Here also we have to remove the 2 electrons remaining. We have is 4f14, 5d1. So this is the electron configuration in Ln plus 2. So after removing of electrons, Ln plus 3 electron configuration. In the case of Ln plus 3, we have to remove the 3 electrons. That means one more electron we have to remove from here. Then the configuration is you already removed the 2 electrons, we have to remove one more electron. This will become 4f1. So remove one more electron, this will become 4f2. Then continuous 4f3, 4f4, 4f5, 4f6, 4f7. Here we have to remove electron from the d orbital. So 4f7, this is a 4f8, 4f9, 4f10, 4f11, 4f12, 4f13, 4f14. So this is the electronic configuration of these elements in plus 3 oxidation state. Electronic configuration in plus 3 oxidation state. This is the electronic configuration in plus 2 oxidation state. This is the electronic configuration of lanthanides in neutral without removing any electrons. So this is the electronic configuration of lanthanoids. So general configuration of these elements plus block elements is n minus d of 1 to 14, n minus d 0 to 1 and ns2. So if you want to write the general configuration of these block elements, n minus 2. Here we are taking outermost energy level. What is outermost energy level? 6s is there. So 6s is there. Then you can take 6 minus 2 f1 to 14. I am writing for lanthanides. And n is equal to how much? 6 minus 1 d, so space is not sufficient. 6 minus 2 f1 to 14. I am writing the general configuration of lanthanides. 14 and n is equal to how much? 6. 6 minus 1 d 0 to 1. N is equal to what? 6s2. Then 6 minus 2, that is equal to 4f1 to 14. 4f1 to 14. 6 minus 1, 5d 0 to 1, 6s2. Look at this. This is the general electron configuration of lanthanides. General electron configuration of lanthanides. So we have 4f orbital, we have 5d orbital. 5d electron may be 0 to 1, and last is almost all have 6s2 electronic configuration. So this is the general electronic configuration of lanthanides. So this is the electronic configuration of lanthanides. Next, atomic and ionic sizes. So atomic and ionic sizes decreases from cerium to lutetium. So when moving from cerium to lutetium in a 4f series, atomic and ionic sizes are decreases. This is nothing but lanthanoid contraction. So it is due to the poor shielding effect of one 4f electron by another 4f electron in the same subshell. So the decreasing size is because of a poor shielding effect of one 4f electron by another electron in the same subshell. Atomic and ionic sizes decreases from cerium to lutetium. From cerium to lutetium, nothing but lanthanide contraction. Lanthanide contraction size is decreasing. Lanthanide contraction. It is due to poor shielding effect of Full shielding effect of one 4f electron. Full shielding effect of one 4f electron by another in the same subshell. In the same subshell. What is this point meaning is, suppose I'm taking this is a nucleus. This is a nucleus. Clear? Then this is the first shell. I'm taking 4f series. So this is the second shell, and this is the fourth shell. This is the fifth shell, and this is the sixth cells. There are 6 cells present in the 4f series elements. So lanthanide, nucleus. So where the first shell, second cell, this is n is equal to 1, n is equal to 2, n is equal to 3, 4, 5, 6. Here is the 4f orbital is present. This is the 4f orbital. Next, this is the 5d orbital. And here is the 2 electrons. They have general configuration is 4f1 to 14, 4f1 to 14, 5d 0 to 1, 6s2, isn't it? 6s2. So in outer motion level there are 2 electrons. Here is 1 electron is there, here is another electron is there. It's clear. So here is 1 electron, this is another electron. So here is the nuclear charge. So cerium to lutetium. Cerium to lutetium, what is the nuclear charge? The nuclear charge is going to get increases. Z effective. Nuclear charge is going to get increases, isn't it? Nuclear charge is going to get increase from cerium to lutetium because atomic number increases, number of protons increases. So number of protons increases, nuclear charge is going to get increases. From cerium to lutetium, nuclear charge is increases. Nuclear charge increases, each unit increasing of nuclear charge by 1 unit, now 1 electron is going to get increases. So that electron is adding in the 4f cell. The electron is adding in the 4f shell. So this nucleus pulling this electron, outer motion electron very strongly towards its nucleus. This nucleus is pulling this electron strongly towards its nucleus because the nuclear charge is increasing. But what is electron added in the 4f orbital? Electrons are adding in the anti-penultimate shell, not in the valence shell. Electron in the 4f series, electrons adding in the anti-penultimate shell. Here is electron is adding. So electron is each element electron adding in the 4f energy level. So here is nucleus attracting the strongly towards nucleus attracting this electron strongly towards itself. But here, what is the present electron in the inner shells? This is inner shell electron. This is not repelling this electrons very strongly. Electron must be get repulsion, but this electron is not repelling this electron very strongly. As a result, this electron coming towards nucleus. As a result, size gradually decreases. So cerium to lutetium, cerium to praseodymium, neodymium, cerium to praseodymium, neodymium, and electrons keep adding. So electrons are adding, nuclear charge also increases. Number of electrons increases in the F shell. In addition to that, nuclear charge also is going to get increases. Here nuclear charge increases, these electrons not repelling the outer motion level electron. These electrons, there is a repulsion between the inner shell electron of electrons present in the 4f shell and outer motion electron. There is no repulsion. So that I wrote here is a poor shielding effect. They are not repelling, poor shielding effect. So because of the poor shielding effect, here nuclear charge is increased. So nuclear charge increased, inner shell electrons are not repelling. Inner shell electrons are not repelling outermost shell. So this nucleus attracting this outermost electron very strongly towards itself. As a result, this electron will be coming close to the nucleus. As a result, the size is going to get decreases. This is nothing but lanthanide contraction. Size is decreasing. Nothing but lanthanide contraction. This lanthanide contraction size is decreasing because of what? Due to poor shielding effect of one 4f electron by another in the same subcell. So these 4f electrons are not repelling the outermost energy level electrons. So but nucleus is pulling. Initially is pulling and final is pulling because nuclear charges keep increasing. This increase in nuclear charge nuclear charge is more, but these electrons are not repelling. As a result, the net force of attraction is more towards net force of attraction between the outer motion of the electron and Z effective nuclear charge is more. So attractive forces is very more when compared to these repulsions. As a result, the electron try to coming close towards the nucleus. As a result, size is decreases. This is nothing but lanthanide contraction. This is nothing but lanthanide contraction. Here we can take ions. So I'm taking Ln plus 3 state. Ln plus 3 state. So the size gradually decreases. I'm taking this is increasing number of atomic number. Z is increases. So this is the radii or size. So cerium. So I'm taking the cerium. This is the cerium Ce plus 3. Ce plus 3. Then next one is cerium praseodymium plus 3 and so on. The elements are rough diagram drawing. So look at this. Size is keep decreases. This is the atomic number is going to get increases. Atomic number, you know how much you can take? 58 initially. Then finally we have to take 71. So 58 to 71. These are the different types of element. And degree I am taking is Lu plus 3. Lu plus 3. So while moving from cerium plus 3 to lutetium plus 3, atomic size, ionic sizes are keep decreases. This decreasing is because of lanthanide contraction or nothing but push shielding effect of 4f, one 4f electron by another 4f electron in the same subshell. So this is atomic sizes. What is the statement is in general while moving from top to bottom, that means while moving from cerium to lutetium, while moving from cerium to lutetium, atomic sizes and ionic sizes are decreases due to this is nothing but lanthanide contraction. This lanthanide contraction because of due to pore shielding. So this decreasing size is because of due to pore shielding effect of 1/4 electron by another in the same subshell. Next, let us discuss the consequences of lanthanide contraction. Consequence of lanthanide contraction. Consequence of lanthanide contraction. In that point number 1, the radii of 5D series D at the 5D series is similar to the radii of 5D series is similar to corresponding members of 4D series. Corresponding members of 4D series. Example we can take zirconium and hafnium. So the atomic radii of zirconium and hafnium are almost similar. So zirconium atomic radius is 160 picometers. Zirconium atomic radius is 160 picometers. So zirconium after we have is hafnium. Zirconium is after we have hafnium. So this is belongs to the 4D series. This is 4D series. Hafnium is 5D series. So zirconium is a 4D series element. Hafnium is a 5D series element. So zirconium atomic ionic radius is size is 160 picometers and its size is 159 picometers. The sizes are similar. So due to lanthanide contraction, the radii of 5D series, the 5D series element similar to the corresponding members of 4D series elements. Example: zirconium and hafnium. Zirconium is 160 picometers, hafnium is 115 picometers. Both are similar sizes. This is the first one. The second one is they have very similar. They have very similar physical and chemical properties. Physical and chemical properties. They have very similar physical and chemical properties. Of course, in any group, physical and chemical properties will be the similar. So, any group physical chemical properties are nearly similar, but here physical and chemical properties are similar, so more than expected. What we are expecting the physical and chemical properties, more than that they are similar. This is due to the lanthanide contraction. Next, the occurrence occurrence together. They occurs together in nature. They occurs together in nature and difficulties faced in their suppression. Difficulties faced in their suppression. These are the some consequences of lanthanide contraction. These are the atomic and ionic sizes in general. So while moving from cerium to lutetium in a 4f series, atomic and ionic sizes are decreases. This is due to poor shielding effect of one 4f electron by another in the same subshell. This is atomic and ionic sizes. Next, oxidation states. The common oxidation states of lanthanides is +3. The common oxidation states of lanthanides is +3. The common oxidation states of lanthanides is +3. So in addition to the common oxidation states, some elements will show the variable oxidation states. Some elements will shows +2 and +2 and +4 oxidation states. In addition to the +3 oxidation state, some elements will show +2 oxidation state and +4 oxidation state. So let's look at the example. What are the elements show the +2 oxidation state and what is the +4 element show the +4 oxidation state? Then I'm taking ytterbium, europium taking EU. So UU, its electron configuration is xenon 4f7 6s2. So europium electron configuration is xenon 4f7 6s2. If europium lost these two electrons, if they lost these two electrons, the number of electrons become in the F orbital is 7. That means they will reach half field electronic configuration. So total possibilities 1, 2, 3, 4, 5, 6 and 7. So 1, 2, 3, 4, 5, 6 and 7. If it lost these two electrons, the configuration become xenon. I'm taking EU plus 2 configuration. So EU plus 2 configuration 4f7 6s0. 4f7 6s0. So look at here. After losing of 2 electrons, they reach half field configuration. 1, 2, 3, 4, 5, 6 and this is 7. So 1, 2, 3, 4, 5, 6 and 7. So it will reach as half field electron configuration is stable. So EU plus will exhibit europium exhibit +2 oxidation state. Let us take one more example. I'm taking ytterbium. So ytterbium is xenon 4f14. This is 6s2. So after losing of the electrons, this will become Yb plus 2. Ytterbium plus 2 oxidation state. They are showing +2 oxidation state. So here is the combination is 4f14 6s0. 4f14 6s0. So look at it has completely full electron combination. 1, 2, 3, 4, 5, 6 and this is 7. So 1, 2, 3, 4, 5, 6 and 7. Total we have to take 14. So look at here. It has completely full electronic configuration 4f14. This is half full electron configuration. This is completely full electron configuration. Both are stable electron configuration. So that these elements will show the +2 oxidation state and the EU plus 2 and ytterbium plus 2. They will show the +2 oxidation state. Next, +4 oxidation state. The +4 oxidation state exhibited by the cerium. I am taking an example. Cerium +4. Cerium configuration is xenon. So what we took here is xenon 4f. Cerium is 4f1 5d1 6s2. So xenon 4f1 5d1 6s2. If Cd will lost to these 1, 2 and this is to total 4 electrons, the Cd will become a cerium plus 4. Cerium plus 4. The combination is xenon, so 4f0, 5d0, 6s0. If you look at this combination, what is the point to understand is after losing all electrons, it getting a plus 4 oxidation state. It is getting plus 4 oxidation state. In this plus 4 oxidation state, xenon it reaching the noble gas combustion. Noble gas is xenon. So 4f0, 5d0, 6s0. So it reaching the noble gas configuration. So that it will show the plus 4 oxidation states. So the point is the common oxidation states of lanthanides is plus 3. In addition to the plus 3, some elements will show plus 2 oxidation state and plus 4 oxidation, nothing but a variable oxidation state. Example, Eu plus 2 and ytterbium plus 2, and next one is cerium plus 4. So this is oxidation states of lanthanides. Next, general characteristics of lanthanides. In that first point, lanthanides are silvery white soft metals and tarnish rapidly in air. Lanthanides are silvery white soft metals, and tarnish rapidly in air. And the next point is hardness increases. Hardness increases with increase in atomic number. The hardness increases with increasing atomic number, and samarium being steel hard. Samarium, Sm being steel hard. The next point is they are good conductors of heat and electricity. Of heat and electricity. They are good conductors of heat and electricity. And the next point is melting point ranging from 1000 to 1200 Kelvin. And the melting points ranging from 1000 Kelvin to 1200 Kelvin. So 1000 Kelvin is to 1200 Kelvin, and samarium melts at 1623 Kelvin, and Sm melts. Samarium melts at 1623 Kelvin. At 1623 Kelvin. Samarium melts at 1623 Kelvin. Next, their ionization enthalpies. IE of these elements around 600 kJ for. IE1 around IE1 of these elements around IE1 of these elements around 600 kilojoule for mole, around 600 kilojoule for mole, and IE2 of these elements is 1200 kilojoule for mole, and IE2 of these elements around 1200 kilojoule for mole. IE2 of these elements is around 1200 kilojoule for mole. So these are the some general characteristics of lanthanide elements. Next, some applications of D and A block elements. In that first one, Iron and steel are most important construction material. In the construction, we will use mostly iron and steel. So iron and steel are the most important construction material. This is the first application. The next one is some compounds are manufactured for special purpose, such as, for example, we can take in pigment industry we can use titanium oxide. So titanium oxide for the pigment industry. In the case of manganese dioxide, in dry battery cells, to prepare the dry battery cells, we can use manganese dioxide. So some compounds are manufactured for the special purposes, such as titanium oxide for the pigment industry and manganese dioxide MnO2 for the use in the dry battery cells. This is another application. Next, look at the next application of the group 11 elements are still worthy of being called coinage metals. So group 11 elements are nothing but copper, silver, gold. Copper, silver and gold. So copper, silver, gold are the coinage metals. So copper, silver, gold are the coinage metals. They are used for the preparation of coins. Next, many metals and their compounds are essential catalysts in chemical industry. Let us take one example. In the manufacturing of sulfuric acid by contact process. In contact process, sulfur dioxide react with oxygen to form sulfur trioxide. So SO2 plus O2 gives rise to SO3. So now this 2 SO2 plus O2 gives rise to 2 SO3. Here we will use vanadium pentoxide B2O5. B2O5 is a catalyst. So in the manufacturing of sulfuric acid by contact process, we will use vanadium pentoxide. Here D block elements, here is vanadium is a D block element and its compound of D block element, it is used as a catalyst. It is as a catalyst in the manufacturing of sulfuric acid. Manufacture of sulfuric acid in contact process. So in contact process we will use vanadium pentoxide as a catalyst. Let us take one more example. In the manufacturing of ammonia by Haber process. We can use iron as a catalyst. Let us look at the equation. I am taking N2 plus 3H2 gives rise to 2NH3. So N2 plus 3H2 gives rise to 2NH3. Here we will use iron as a catalyst, molybdenum as a promoter. So iron as a catalyst and molybdenum as a promoter. Here iron is the D block element. So in the manufacturing of some chemical compounds, we will use D block elements as a catalyst. This is a manufacture of ammonia. Manufacture of ammonia by Haber's process. So manufacture of ammonia by Haber's process. Let us take one more example better understanding in the hydrogenation of oils. Suppose I am taking vegetable oil. So hydrogenation, H2. So in presence of nickel as a catalyst. So hydrogenation of vegetable oils in presence of nickel catalyst gives vanaspati, vegetable ghee. This vegetable ghee is nothing but vanaspati. Nothing we are calling it as a dalda. So here is many metals and their compounds. Here is nickel is a metal, iron is a metal. Many metals and their compounds. Here is V2O5 is a compound. Many metals and their compounds are essential catalyst in a chemical industry. Example: manufacturing of sulfuric acid by contact process and manufacturing of ammonia by Haber's process and manufacturing and conversion of vegetable. Here the point is vegetable oil is converting into vegetable ghee, hydrogenation of vegetable oils. So this is some applications of D and A block elements.